Good afternoon and welcome to Live from NOIRLab at Arizona. I am your host today, Rob Sparks, with our moderator Jamaica Marshall and our guest Joan Najita. Joan is an astronomer at NOIRLab and going to give a talk, A Sleuth Among the Stars, uncovering the origins of stars and planets. And I'm very much looking forward to this talk because it's a very interesting topic and she is a very good speaker. So first, I'd like to tell you a little about Kitt Peak National Observatory, where we're located in Arizona, the facility we run, which you can see a snow-covered version of it behind me. Yes, we got snow in Tucson yesterday, so this is a view from the webcam from about 15 minutes ago. So Kitt Peak National Observatory is funded by the National Science Foundation and is a NOIRLab facility. It was founded in 1958, and is located about 55 miles southwest of Tucson on land leased from the Tohono O'odham Nation. We are indebted to the O'odham people for letting us use one of their sacred mountains for astronomical research. Kitt Peak is home to over 24 optical telescopes and 2 radio telescopes as well. Now we always start out with a little recent science highlight, and announced last week at about 2 weeks ago, at the American Astronomical Society meeting, is this detailed map of brown dwarfs. Astronomers have curated the most complete list of nearby brown dwarfs to date, thanks to discoveries made by thousands of volunteers participating in the Backyard World Citizen Science Project. The list in 3D map contains 525 brown dwarfs, including 38 reported for the first time. This discovery incorporated observations from a host of astronomical instruments, including several NOIRLab facilities. The results confirm the Sun's neighborhood appears surprisingly diverse relative to other parts of the Milky Way galaxy. Aaron Meissner of NOIRLab was a guest on a previous edition of Live from NOIRLab, where he talked about backyard worlds in the project. And so if you'd like to watch that, you can do that on our YouTube channel and learn how you can become involved in backyard worlds, and maybe you will discover one of these brown dwarfs in the future. So that's a great podcast, and we'll put the link in the show notes when this edition of Live from NOIRLab goes up tomorrow. Without further ado, I'd like to introduce our guest, Joan Najita. She received her undergrad degree at Harvard and majored in physics and astronomy, her PhD in astronomy from the University of California, Berkeley, and she previously worked at the Space Telescope Science Institute before joining the National Optical Astronomy Observatory in 1998, which of course has now become part of NSF's NOIRLab in 2019. She has a wide variety of research interests, including the origins of stars and planets, exoplanets, low-mass stars and brown dwarfs, the Milky Way, infrared spectroscopy, massively multiplexed wide-field spectroscopy, the nature of discovery in astronomy, science, sociology, and resource allocation practices, science communication strategies, and the role of science in society. I get tired just going through everything she does in this presentation here. So, Joan, if you'd like to come on, I'd like to welcome Joan Najita. Hi, Joan.
I'm muted. Hello there. Thanks, Rob. Thanks,
You're welcome.
Jamaica.
Yes, and Jamaica, please, just a reminder, please feel free to put your comments in the chat, and Jamaica will relay them to Joan. So at this point, I'd like to invite Joan to share her screen and start her presentation. So, like I said, please put any comments or questions in our chat, and I will mute out here.
I hope you can see my slides. Rob asked me to share something about the kind of research that I do, and so I wanted to do that and also share a few things about myself as a person and also about the kind of work that I do at NOIRLab. So you may know a lot of other astronomers, and many of them are the kind of people who always wanted to be an astronomer, maybe built their own telescope, had their own telescope, know the sky like the back of their hand. That wasn't me as a kid. I was just the kind of person who likes science and likes to figure stuff out. So one time when I was as a high school student, I got together with some other high school students in my hometown of Honolulu, Hawaii. And on the weekend at a high school, and an astronomer came to visit us and tell us about what the Voyager spacecraft was observing at Jupiter. And it was kind of mind-blowing. Jupiter looks so amazing when you can see it really close up. And some of the images were just truly beautiful. So much detail and so awesome. all these intricate structures, or this one, another beautiful image. So it was amazing to me how you could study something so beautiful and so interesting and get paid for it. So I asked the speaker whether it was something that a student might get involved with. And one thing led to another, and soon I had a summer job observing at the summit of Haleakala on Maui. Haleakala means house of the sun, and so very appropriately, there I was as a daily observer, rising with the sun and following it across the sky and capturing its changing face. It was so amazing. I studied, as Rob mentioned, I studied physics and astronomy in college, and I was lucky enough to be invited to be a summer student at Kitt National Observatory one year, where I fell in love with the desert and the wonderful people at the National Observatory, so kind and welcoming, the wonderful research, and I loved the mission of the observatory, which is to make possible anyone with a good idea to carry out an interesting project with our facilities. So when the opportunity came up a few years later to join the National Observatory, I was eager to do it, and I've been here ever since. So what do I do in my job? I think my mother often wonders this, and she probably imagines that I stay up really late at night. Maybe I'm at the top of a mountain. Maybe I'm staring out the slit of the dome or something. Well, it's actually, there's a combination of research and what we call observatory service. So as Rob already mentioned, some of my research interests are things like the origins of stars and planets, the origin of our Milky Way, our galaxy, and many other things. Astronomers like me use multiple techniques. I use theory in the form of using ideas from chemistry to understand the nature of things. There's observing too. And one of my favorite things is spectroscopy, where you disperse the light into different wavelengths and hunt through the different wavelengths to find out the information about the object that you're looking for. I particularly like to look at photons that come from wavelengths longer than our eyes can see, so at infrared wavelengths. And I also like to use what's called wide field spectroscopy, where you observe take the spectra of many objects all at the same time and try to figure out from the ensemble of information what we're looking at. Turns out that sometimes you can make an interesting discovery without doing any new theory, without doing any new observing, and just using archival data, stuff that people have already collected, just thinking about it in a different way. And surely one of the most important techniques, most important tools that we as scientists and astronomers have is to keep an open mind to new ideas and keep our eyes open for new opportunities and new interpretations. So in addition to all of the research, we also do observatory service, which is to contribute to the mission of the observatory, which is to enable anyone with a good idea to make a discovery. And some of the things that I do in support of the observatory are strategic planning. What kinds of new initiatives and instruments, facilities, or programs should we do? And also communications, outreach to our science community and to the general public. So that's just a little bit about me, but now I wanted to move on to the topic that Rob asked me to talk about, the origin of stars and planets. And what does this mean? Basically, it means trying to figure out what is the very early life history of stars and planets. Now you might think that's a kind of odd topic. When I look up at the sky at night and I see these beautiful stars, they seem like they've been there forever. What kind of story do they have? Well, as we also know, it's a triumph of the physics of the last century that the understanding that stars aren't eternal, but that they do evolve. So a star like the sun may start its life like this, but become a red giant and evolve into a planetary nebula, and eventually transform into a glowing, glittering pearl a white dwarf that slowly cools and fades. So the question for me, people like me, is what's the backstory of all that? What happens before? How did the sun get to become a star? How did it begin? What is the beginning of its story? So astronomers have lots of stories about that. And here's a quick cartoon version of the story. So the story begins in molecular clouds, where clouds of gas collapse under gravity and start infalling onto a stellar seed. The material in the cloud has too much angular momentum. So you can't just make a star, but a lot of the excess angular momentum goes into orbit around the star in a circumstellar disk. The material in the disk swirls onto the star, and the star eventually says, I've had enough, and it launches a wind that blows away the surrounding molecular gas, leaving behind a formed star, mostly formed star, and a disk. This disk could make some planets and do other things, and that's the basic story of how a star is born. So that's a great cartoon, but can we actually see any of this really happening? The story starts with molecular clouds. And what are these? These are clouds of gas and dust that also happen to have molecules. You've probably seen some of these, perhaps on a calendar or a mug or a mouse pad. This, for example, is the famous Pillars of Creation in the Eagle Nebula M16. And what's happening here, these are the molecular clouds here, and stars outside the clouds are shining their powerful rays onto the molecular clouds and making them glow on the outside. You probably have also seen this molecular cloud. The molecular cloud is down here, and energetic photons from stars are shining onto the surface of the cloud, producing the well-known Horsehead Nebula in Orion. Here's another molecular cloud, one that I really like. It's an Ophiuchus, and you can see these cloudy materials here, again with bright the fluffy outer parts of the cloud have been lit up by surrounding stars. But perhaps my favorite molecular cloud is the Taurus molecular cloud. So if you look up in the direction of the constellation Taurus, you'll see something that has a lot of stars in these dark lanes here. That's the Taurus molecular cloud. And here's another version of it, where it really does look pretty cloudy. These dark clumps in the middle of the cloud are the ones that are that are in the process of making stars. So here we have some examples of the molecular clouds from which stars form. What about the forming stars themselves? Can we see them? Well, quite some time ago, the Hubble Space Telescope snapped these pictures of some forming stars. And you can see that just like in the picture, in the cartoon, there's a star in a disk. HST saw a star surrounded by a dark disk of material. That's the dust that's absorbing the nebular light from the Orion Nebula. And if you turn that on its side, you can see that these disks are really quite flat and they're pretty round. So one of the things I wanted to share with you today is some of the things that we can do what we can learn by studying these kinds of structures, and give an example of how we can get some insight into the origin of life on Earth, looking for evidence of the chemical building blocks of life, and looking for evidence of actual ongoing planet formation. On the first topic of the origin of life on Earth, here we are on the surface of the Earth, and there are people and animals and all kinds of other living things. And life is created through the workings of complex molecules. Well, where do these complex molecules come from? What were their chemical building blocks? The prebiotic molecules, where did they come from? Astronomers and astrobiologists have different explanations, or have entertained different explanations over time. One group of explanations is that it's a the Earth comes as a complete package. It comes with its all the ingredients needed for life already combined. You just have to press go or turn on the microwave and just heat and serve, and life happens. Another bunch of ideas are that the Earth didn't come with all the ingredients that it needed, and kind of like Hamburger Helper, you had to add some other stuff in order to make it happen. Now, in the picture of the first one, where it's self-contained, that one of the ideas that sparked that comes from the well-known Miller-Urey experiment. And it's really quite clever that people took a laboratory apparatus and put some water in it. There's water vapor. You add some gases that you think the early atmosphere of the Earth was composed of, so methane, ammonia, and you make an atmosphere, and then you give it some lightning, maybe a spark. And then you let the material cool, and wow, amino acids have formed. So it seems pretty likely, if this was how it really worked, that you could make the building blocks of life in a self-contained way. But as people thought about the early Earth more carefully, they found that the early atmosphere was not really made of ammonia and methane, but was made of other things like carbon dioxide and molecular nitrogen. And when you have those molecules, the yield of amino acids is much lower. And so it seems really unlikely that it's really a heat and serve kind of answer. So today, astronomers really think that much of the chemical building blocks of life, the prebiotic molecules, were probably synthesized in molecular clouds and circumstellar disks, and then delivered to planetary surfaces by bombarding asteroids and comets. We have a little bit of evidence for that when we look at things in our own solar system. Comets have complex molecules, and if we do some analyses of meteorites, we find that they have complex things like amino acids in them. So how common are these building blocks, and do they occur in other systems? One way we can answer that kind of question is by following the story backwards and looking to see what kinds of molecules are present in circumstellar disks. So we had a chance to do something like that many years ago, maybe more than 10 years ago, when the Spitzer Space Telescope was in orbit. That's the infrared version of the Hubble Space Telescope. And because it could observe at the right kinds of wavelengths to look for these prebiotic molecules, we were hoping to be able to look at these kinds of disks. Now, most people were pretty pessimistic about that. They thought that disks, we could only see the dusty components, these dark components in the disk, but the gas in the disk might be too hard to see. But we persevered anyway. And we were really surprised and happy to find that these disks really had there was a lot to observe. So if you take the mid-infrared light from these disks and you spread it out in the spectrum, this is what we saw. Many lines of water from these disks, as well as organic molecules. So here's band heads, bunches of lines of the organic molecule acetylene. There's another band of the organic molecule hydrogen cyanide. There's also carbon dioxide. Ammonia is also detected. And if you do things like if you have water and hydrogen cyanide and ammonia, you shake it together, you get amino acids. And so you can see that disks really have a lot of the building blocks that are needed for life. And so that kind of observation is one of the ways in which we can help to put this picture together and test it out. And so far, it looks like disks really are, the planet formation environments really do come with prebiotic molecules. So when you look up at into Taurus, one night in the sky, it's kind of interesting to think that prebiotic molecules are being made there. But we can also look at these same disks for some other kinds of insights, perhaps into understanding whether any of these stars that we can see are actually forming planets. Now, astronomers also have a good story going about planet formation too. It's called the story of core accretion. The story goes like this. The story of planet formation begins in a disk that's made of gas and dust. And the dust is very small, micron-sized. These dust grains grow and stick together, becoming larger and larger, and eventually collective effects end up making really large rocks, like a kilometer in size, things called planetesimals, things that are like comets. These planetesimals can collide and grow to make things even larger, thousands of kilometers in size, protoplanets, like the moon and Mercury. And if these protoplanets collide and grow, they can make something really big, like a 5 to 10 Earth mass core, something like an ice giant in our solar system. And if these cores grow quickly enough, they can accrete a gaseous envelope and make a giant planet like Jupiter in our solar system. And eventually the disk goes away and we're all done. If we got to the end of the story, we might have made a gas giant. If we stopped earlier, we might have made an ice giant. If we stopped even earlier than that, we might have made a terrestrial planet. So you can see that this is a very inclusive picture. It includes, there's a role for pretty much everything that we know about, from small grains that we see in the interstellar medium, to the bigger grains we catch with our spacecraft, to comet-sized objects, to protoplanet-sized objects, to Earth-sized objects, and if we keep going, to ice giants and even gas giants. So people really like the core accretion picture because it can pretty much explain everything that we know about the solar system. It has the rocky terrestrial planets and a way to understand the giant planets. And because it explains this wide range of planetary masses and sizes, it could potentially also explain a lot of the things that we see, that we know about exoplanets. So if we look at a distribution, what kinds of planets are found around other stars as a function of their mass and their separation, the distance from the star, we see that there's all kinds of interesting planets here. There are Jupiter mass planets that are kind of like at Jupiter distances, but also Jupiter mass planets that are much closer, hot Jupiters. There are Neptune and ocean worlds and ice giants that have the masses of the ice giants in our solar system, and also planets that have the same kinds of masses and sizes as the terrestrial planets in our solar system. And because the core accretion picture can explain this wide range of kinds of planets, it provides a framework for us to understand where these exoplanets come from. So today we've been discussing two different stories, the story of star formation and the story of planet formation. An interesting question is, how do these two stories fit together? Is it stars form first and planets form second? So like volume 1, volume 2, or is it something else? Now you can see in the way that this picture has been drawn here, the star is really forming first, and then maybe planets are forming later. And that has been the mental picture of star and planet formation forever. But as these discoveries were rolling in over the past 10 years, and more announcements were made that there's a lot of planets here, every star is a planet, lots of planets, it made me wonder whether this picture could really hold up. Because when we look at the disks that we know and love, the ones we can see, and we've been measuring their solid masses all this time, it just didn't seem to, it seemed very difficult to explain all these planets that people were discovering could really come from the small amount of solids that are present in disks. In other words, if you do an inventory of all the solids in exoplanets and you compare them to all the solids that we can see in disks, the disks are underweight. Now, why is that? It's actually a sign of planet formation. And the reason is, at the very beginning of the story, when the dust is really small, you can see all of it. You can count everything. You can see exactly how much of your planet building material you have. But as planet formation goes on, you're taking the small things and making large things. And that makes those things very hard to see. example, if you take a piece of tin foil and you pound it really thin so it's only a micron in size, it's going to be a really big piece of tin foil. And if you put it out and you let the sun shine on it, that piece of tin foil is really easy to see from far away. Now take that tin foil and crush it down to the density of a rock. It's going to be a lot harder to see because its surface area is going to be really small. If you put it at the same distance, it'll be really difficult to see. And for that very reason, as planet formation occurs, those solids become harder and harder to see. And that's the reason that they appear so underweight. You really have a lot of solids. It's just that they've actually grown into really big things, like maybe planetesimals or protoplanets. So what that says is that the disks that we've been observing all this time, where we've been laboring under the idea that they're any day now, they're about to make some planets. In fact, no, that's not the story. They're well along their way in having already begun the planet formation process. In other words, we've got the story, we have to rewrite the story a little bit. It's not that stars form first and planets form second. Planets are really forming along with stars. So as the star is being built, planets are also forming. And that intertwined nature of the formation of stars and planets is an interesting and also challenging picture. It challenges our understanding, our story of how planet formation really begins, the physics of how that really happens. Now, this is an interesting insight that you can get by not having to take any data yourself. All the measurements that we needed, the masses of planets, the masses of disks, were already made by other people. And so this is an example of some new insights that one can get by just working with archival data. Now today, when you think about this picture, you might think, doesn't seem so amazing. Well, way back when we proposed it in 2013, this was a kind of revolutionary. Like we felt we were really going out on a limb to say that the story of star and planet formation, it's wrong, we have to rewrite it. And one of the reasons why you may be thinking that it's not so impressive is because of the advances that have been made since then. So in 2013, this was a revolutionary idea, but only a few years later, it was more or less confirmed with observations made with the Atacama Large Millimeter Array, which is a set of millimeter dishes, an interferometer on the Chajnantor Plateau in Chile. And so in 2015, ALMA was getting going and it released this image. You may have seen this image before, and they, even though ALMA was a relatively new facility, immediately declared that this was its best image ever. And it was amazing. When I saw it, I thought, is that a simulation? Because it looked exactly like our cartoon pictures of what we thought planet-forming disks might look like. When disks form a planet, they clear out a region around it, partly because they're grabbing all the dust close to it, but also because if it's massive enough, it can push away material in the vicinity of its orbit and carve out these dark rings. And what's interesting about this image of HL Tau is that these dark rings, which are like footprints of planets, are on the size scale. Some of these rings are on the size scale of the giant planets in our own solar system. Some of these rings, though, are at larger distances than the planets in our own solar systems. And so they would point to planets if these rings are really due to planets residing at even larger distances than the planets in our own solar system. Now, this is just one observation made with ALMA, but in the intervening years, many other observations have also been made, and they've shown a lot of amazing structure. So those kinds of gaps and rings seen in the HL Tau image are not unique. We see many other similar kinds of features surrounding many other stars. Some rings are very narrow, some are thicker. Sometimes there's a lot of contrast or less contrast. Sometimes they even have these sort of spiral patterns here. Very few of them are actually smooth and featureless. Almost everything has some kind of structure pointing to some kind of planet formation. So these disks are not the unevolved structures that we always had imagined them to be, but they're highly evolved. Now, one of the things that could be creating these structures that we see are planets. And so some of my friends have made simulations of what might be happening. And so in this picture, we're going from early time to late time, and the star is this green dot, and the planet is this green dot. And as it orbits, it ends up creating these very deep multiple gaps. So a single planet could create multiple gaps. And so part of the problem that we're faced with is trying to figure out what these structures are telling us, what kinds of planets and how many planets might be present here. The structures that we see are actually incredibly diverse. And here's another look at some of them. So this is the image that we just looked at, the collection of disks. And here's another bunch of disks. Many of them are big rings. When we look at similar kinds of structures seen at optical wavelengths through scattered light, we also see wonderful two-armed spirals. So there's a lot of new substructures that people are discovering. And one of the most interesting things in this field is trying to figure out what kinds of planets are forming and where are they. When we try to figure out what kinds of planets may be creating the structures that we see, theorists can make many predictions about what kinds of planets might be out there. The current ideas point to an even greater diversity of planetary systems than we had previously imagined. So before, when we were looking at this diagram of planet mass versus semi-major axis, so distance from the star, we were talking about how there's a population of Jupiter mass planets at Jupiter distances, how there's hot Jupiters at smaller distances, how there are ocean worlds and ice giants, and terrestrial planets. The planets that are implied by all these structures that we see here are typically at solar system or larger distances, and they range from ice giants to giant planets. So showing that that these other solar systems have similar or larger mass planets at similar or larger radii than the planets in our own solar system, pointing to, again, the incredible diversity of the outcome of planet formation. So many of those sources that we were just looking at are actually in the Taurus molecular cloud. So the next time you're out at night looking up at Taurus, it might be fun to think about how some of those stars are not only forming planets, but also some of the prebiotic molecules that are the chemical building blocks of life. So what's going to happen to these systems in the future? Will they actually produce any living organisms? We'll have to wait and see. Now, just to end here, I wanted to share one more thing about what it's like being an astronomer. And I wanted to go back to the title of my talk. The first part of the title was A Sleuth Among the Stars. What does that mean? Well, I hope I was able to illustrate some of the different ways in which astronomers do their research. Sometimes they're like a detective, like Miss Marple, and sometimes they're like an author, like Agatha Christie. We're detectives when we are given a case, we know what the problem is. Like, are there prebiotic molecules in disks? Aha, I know what I'm looking for. And you go ahead and you do your detective work, you keep your eyes open for opportunities and unexpected clues, and then you try to put the pieces together to solve a problem. But sometimes we have to do some different kind of work where it's not so much where we are given a question and we solve it, but sometimes we have to think about what is the question, what is the problem, and we have to write the story or rewrite the story of whatever's happening. So for example, when we wanted to know about the question of whether stars form first or planets, how are these two things related? That's an example of writing or rewriting the story. And so those are some of the things that keep me busy at NOIRLab. Thanks.
Much, Joan. That was great. So I think we also learned something else about you toward the end, that you like murder mysteries.
So true.
Yes, I do theater, and many years ago I got to be in Agatha Christie's *The Unexpected Guest*, the stage play. So that was a lot of
Ah,
fun there. And that's the one work of hers I know the best, forward and backward, to say the least. So, Jamaica, do you have any questions or comments you'd like to share?
Um, we have had a question here from Alan Jackson, and Alan asks, what does SHARP stand for on the title of one of the planet forming slides?
that's a great question. And I have to admit that I can't remember exactly what it means. It's an acronym. Let me go back to the slide. D sharp. It's a clever acronym, maybe for musically inclined astronomers. But it's the name of their collaboration that produced these images. And I believe we'd have to check it out in the AppJ paper, but I believe D stands for disks. And I'd have to guess, but it might be super high angular resolution program, because the imaging that produces these incredibly narrow disks uses very high angular resolution. So they're using ALMA in its most extended configuration to produce these this very detailed picture.
I just Googled it, Joan, and you're right on target. It's disk
Really?
substructures at high angular resolution project. So you're right on target. High angular resolution to stuff right there. So yep.
Okay, and then we also had a comment earlier on, several, from Joel Riverboat, who says, thank you so much for this great presentation. And he also thanked us for making these available to the general public on YouTube. So thank you all who are joining us and been engaged with Joan's presentation here. And yes, we are happy to make these available on the NOIRLab YouTube channel.
And I'll just mention that when you talked about the Taurus molecular cloud, I just did a quick Google search of images people have taken of it, and found some images people have done with DSLRs and 18 to 55 millimeter zoom lenses. Now, granted, with a lot of exposure time, but there are some lovely images I found just Googling quickly, and I said, now I'm inspired. I want to try that. I've never tried that imaging that part of the sky at that depth before, so now I want to see what I can do with that and see how close I can come to reproducing some things they did. Of course, the best image I saw was 12 hours of exposure time granted, so were fairly serious. But still, it was a Canon, a camera and a zoom lens. That they got that image. It was amazing.
Oh, that's wonderful.
So with that being said, Rob, Joan, what kind of images, if let's say, Rob and I were out, we have our telescope and we have the camera pointing towards Taurus with a wide field of view, what kind of images could we expect to see compared to, the kind of images that you were showing us?
Oh, well, let's see. Let's go back to some of those. Somewhere back here. Oh, is there an easier way to do this? Yeah, so this is the digital sky survey. So it's taken with a pretty big telescope, but awesome. And I'm not sure. I don't recall exactly where this image comes from. So I can't really say. But some of these, and of course this one is taken with the Hubble Space Telescope. But you can see a lot of the structure in M16 just with a much smaller. You don't need the Hubble Space Telescope to see all that, to get all these beautiful colors and the detailed features from these different emission lines. That's really the magic, and of course the high angular resolution. But just the idea of these structures and sort of what they look like, you can get that with just by looking.
I really love how this science still through astronomy is approachable for the everyday person with, if you can afford some equipment, use it, borrow it at your local observatory or planetarium, once, things are back to normal, then that you could also get a glimpse of this on your own without all of this extra fancy equipment and an expert like you at their side, but they could still look on their own and glean some of this information on their own. And that's really empowering. Thank you for sharing that with us.
Sure. Yeah, that's one of the fun things about studying star formation, that many of the well-known things that that people are aware of from just because they're beautiful images are also the things that where the action is occurring. So that's one of the things I really love about it.
And we also have another question. If you if we can give you another one, Joan, before we wrap up.
Sure.
Okay, so we have Stephanie, and Stephanie asks, can discs with spiral arms also contain planets?
Oh, great question. Okay, let's go to some pictures of discs with spiral arms. So when you look at a disk like this with its double spiral arms, you might think of something like M51, a galaxy. And when you have these interacting galaxies, one and another one's coming by, and it pulls out the material in the galaxy into these arms. So if you think about what the galaxy pair looks like, the perturbing galaxies up here, if you take this arm and you point away, use it as a pointer, it's pointing to the perturber. So here it's not two galaxies, but it's a disk around a star and something that's perturbing it, and that something is probably a pretty massive planet. So it's sort of like the idea of two galaxies passing by, but here we have a star with its disk and a massive companion, a giant planet, that's creating these same sort of arms. I hope that addressed what Stephanie was asking.
I hope so too. Stephanie, in the chat, if you need some more details for that answer, please let us know. And Joan obviously is happy to provide more details. Yes, thank you. So I'd like to say thank you to everyone in the chat, and we do still have some more time. So Rob, I actually had another question, if I could ask, that's kind of related to the topic in general, and that is about angular momentum. At the beginning of your presentation, you talked to us about you use angular momentum, and at the time I almost popped in to ask you to tell us what that is and why it's so important. So could you maybe tell us a little bit about angular momentum and the role it plays?
Of course, sure. Mass and angular momentum are the two major things in the story of star formation. So let's see, somewhere back here. So the material from which stars form is it's a cloud, but it's also rotating. And so as material falls in, it can't all fall onto the star, so it makes a disk. It's kind of like a classic example from physics textbooks is a skater. But you can pretend that you're the same thing when you sit on a swivel chair in your office or at home. And if you're spinning and you have your arms out, you're going pretty slowly. But if you think about when you watch the Olympics or a skating competition, when the skaters pull in their arms, they spin faster and faster. And that's basically the same thing that here, this cloud is when the skater has the arms out. And as it falls in, the arms are coming in. And so things really spin up. And that's where that's why the disk is spinning so quickly. And at some point in star formation, you can't pull your arms in enough because you reach the limit where you're rotating as fast as you can go. And so that's why the material has to end up making this disk. And to get a sense of what that feels like, try spinning on your chair with your arms out and then pull them in.
Should we demonstrate spinning on our chair with our arms spread out, right? Maybe that's something, if you're in our audience, try that at home when you have cleared out your space. Make sure you be safe. But that is a great way, a great demonstration. Thank you for the suggestion, Joan. But that's really interesting explanation. Thank you.
If you want to have some real fun while doing that experiment, put a heavy book in each arm to give you a bigger change in your rotational inertia. So that'll really make the effect dramatic. Of course, it's also much harder to maintain your balance. So that is a very cautionary tale for people too.
And I think at NOIRLab we're very conscious about safety, so we don't want to encourage anyone to do anything unsafe.
You're absolutely right. Yes.
Well, I taught physics in a different time, apparently.
And so, Joan, really quickly, if I may, for those of us who are in school still, or like me, transitioning from one career into another, do you have anything you'd like to share with us about any experiences you had during your career that you think may help others as they are on their journey in science or in astronomy specifically?
Yeah, sure. I guess, like thinking about some of the things I mentioned today, I think it's important for everyone to follow your passion, the things that make it interesting for you. Like, I'm not like Rob, where I can make beautiful images, I know the sky so well and all that. I just like solving problems and figuring stuff out, and but let that be a strength rather than a negative. It's totally okay to pick the thing that really makes you excited about what it is, and make use of it, as make it your superpower. There's room for so many approaches to science and all that. So yeah, and if anybody would like to chat about it or discuss, my door's always open.
Amazing. Thank you so much, Rob. Sorry. Thank you so much, Joan. Rob, I was going to ask, what do we have coming up?
Yes, Joan, if you could stop sharing your screen for just a moment so I can share mine.
Sure.
Right, so we're going to switch to my screen. Let's see, here it is. This is next week's live from NOIRLab. Will be coming from Gemini, correct, Jamika? And let's see.
Yes, that's correct. Next week is live from NOIRLab at Hawaii. My colleague, Alyssa Leinani Losi, will be your host for Journey Through the Universe. Now, Journey Through the Universe is returning for its 17th year with a week of virtual educational programming from March 1st through the 5th of this year. And so next week's show will be talking about that program. And so stay tuned for sure. It's going to be very interesting and a lot of fun.
Super. Thank you very much, Jamika. So, and thank you very much for joining us, Joan, and sharing all your stuff with us. That was fantastic as well. So,
thanks for inviting me, Rob. It was a pleasure and great to work with you, Jamika.
And of course, if you'd like to rewatch any part of this, we will post the recording tomorrow, shortly, probably tomorrow, with some show notes, I'm sure, as well, with some links to some of the sites that you had in there as well, Jamika. So thank you very much for joining us on this week from Live from NOIRLab, and I would like to sign off at this point and say goodbye to everyone. So, bye.
Thanks, everyone.
Aloha.
Aloha.